recently started a website, the Chip Hopper. Don't really have any plans for the site, but it's kind of starting out as a blog. I work in manufacturing, and I've learned a lot of stuff along the way, and I just kind of want to start sharing information that I've learned and interesting projects, and so we'll see where I go with it. But in today's video, I'm going to talk about calculating the angle of engagement for a milling tool. The angle of engagement is a parameter that you can use to help understand load on a tool. You typically don't ever think about the angle of engagement directly, but anytime we talk about corner machining and load spikes and braking and chatter, the angle of engagement kind of comes into play whether you realize it or not, because when you're machining a corner, the angle of engagement of a tool increases. So anyways, today we're just going to go through the simple derivation and calculation of calculating the angle of engagement of a milling tool going in a straight line. So we'll start with, we'll look at, like I said earlier, milling tool. So it's going to be the spindle view of a milling tool. Get a tool, let's say it's rotating clockwise. Let's go ahead and say it's climb cutting. So this is the path where the material is already cut, cutting this way. So we have our step over. And then we have our tool radius. So we'll go ahead and draw the tool radius to our contact points in the cut. And then we have the parameter we're interested in, theta AE, the angle of engagement. So this is just our direction. Anyway, when you get information from a manufacturer, you're given everything you need to calculate the angle of engagement. Like I said, directly it's not a useful parameter to calculate all the time, but it does come into play when people talk about step over as a percentage of diameter, because when you talk about step over the percentage of diameter, you're actually maintaining the angle of engagement with different tool sizes, so you can actually kind of scale tool load with the size of the tool. So we'll go ahead and break this up into right triangles to help us calculate everything. Since we've broken up this line into a couple pieces, this one is our step over. We'll go ahead and name this one RC, just the leftover piece of the radius of the cutter. So I'll go ahead and try and draw a little line in here. Let's see. Oh, my mistake. It goes right there. I'm going to call that RC. That way we can have a variable for our relationship. So we're going to start with defining the theta AE, the angle of engagement. So if you remember the mnemonic from trigonometry, so TOA. So we know the radius of the tool here. We don't know RC, but we can find it, and we don't know this line, which we can also find, but it's more of a hassle to find, so let's go ahead and not worry about it. So in this case, we're going to use, we know this is the hypotenuse of our triangle. It's the adjacent of the side that we're interested in over here, because that's where theta we're interested in. So in that's the case, we're going to use the adjacent hypotenuse side, which is the ka from SOHCAHTOA. So cosine of theta AE equals adjacent over hypotenuse, so RC over RT. Now, like I said, we don't know RC, but we can find it. So now, since we drew from the stem of the tool these two tangent points, this is the same distance. So RT, this is actually RT on both sides. So we can form the relationship that RT equals RC plus SO, our step over. So we need our C over here, so we'll go ahead and subtract SO from both sides. So minus SO, RC equals RT minus our step over. So now we have an expression that we can plug into our relationship over here. So the cosine of theta AE equals, keep a bad habit of tilting the paper, sorry, and maybe being off center. And plug this in, so we have RT minus SO over RT. Now we can simplify this a little bit by separating the common denominator in this fraction. So if we do, now let's do RT over RT minus SO over RT. You can simplify the expression cosine equals 1 minus SO over RT. Now remember, we're trying to find theta, so we need to take the inverse cosine of both sides. Cosine -1. So that takes us the theta AE free, and you get cosine -1, 1 minus SO RT for our relationship for the angle of engagement of a tool. So we'll go ahead and just go through a couple of examples just to see it in action. So if we go and do, let's say, a 3/8 diameter milling tool. So we got our tool. Let's see. I just like drawing pictures because it helps. SO. So we take our formula that we derived, AE equals cosine -1, 1 minus, so let's do, I've always hear 6% as like a conservative step over calculation. So 6% of 3/8. I'm actually not very good at mental math, surprise, surprise. 225 thousandths step over. So 0.0225 over RT, so that's going to be 3/16 for our tool diameter. Boom. So 28.357 degrees, just round out. So now let's just do another one. Let's say a 1/2 inch tool. So same thing, step over. So let's say just 50 thousandths. 50 thousandths. So theta minus 0.05 divided by 0.25 because this is the radius of the tool. This one calculates to 36.370 degrees. So remember how I told you earlier that using percentage scales the angle of engagement? Let's show that. So let's use the same tool diameter. So use a 1/2 inch diameter tool. We're going to say 6% of the diameter. So that is a 30 thousandths step over, 0.03. If you do, so -1, 1 minus 0.03 divided by 0.25. You get that. You get 28.3 357. I should probably round it up because of the other decimal places, but so you get the same angle of engagement for two different tools. So using percentage helps scale the angle of it maintains the angle of a constant angle of engagement with different tool sizes. So like I said, that helps you basically maintain and control load and keep that load with the tool size as you change tool sizes. Anyways, I hope you find this video helpful. In the next video, I'm planning to calculate a relationship between the step over and a minimum corner radius. This can be pretty helpful if you're dealing with really simple tool paths. Some of the advanced milling cam tool paths kind of deal with this for you, but if you have like a simple tool path that starts in the center and does like constant step overs, sometimes you can define a minimum radius to leave. So what I'll work through next time can actually be a useful tool to kind of figure out, how small should I go, how much does it increase the angle, and things like that. Anyways, I hope you found this video useful, and thank you for watching.